that was one of the learnings here. It's not, it started with performance, but then it became sort of the secret sauce of the company to be able to ship that quickly, because you don't have to do all these things.
Hey, before we get started, I'd like to remind you that the full episode is only available to our subscribers. The current platforms you can subscribe on are YouTube, Spotify, Apple, and Patreon. And with that, let's get on to the episode. Hello, welcome to the DevTools-fm podcast. This is a podcast about developer tools and the people who make them. I'm Andrew, and this is my co-host, Justin.
Hey, everyone. Really excited today to have Tuomas Artman on from Linear. Tuomas, it's such a pleasure. We had Jory on back in episode 44, which is really fun. Excited today to talk about the sync engine, which is, I think, a really both compelling feature of Linear and also just like a deeply interesting technical topic. But before we dive into that, could you tell our listeners a little bit more about yourself?
Oh, yeah, sure. So I'm Tuomas, if you want to pronounce it correctly. Nobody can, so I go by Thomas, anywhere in the world. I'm an engineer by heart. Like, I started my career back in '96, doing CD-ROM multimedia presentations for big corporate customers here in Finland. If you ever had a Nokia phone, that usually came with a CD-ROM with instructions on how to use that phone. Chances are that was made by the company, or even me, back in the day. And the internet came around rather quickly after '96. So I founded my own agency together with a few friends. Still doing Flash animations and campaigns, and then going into sort of your regular web agency. And it took me 9 years to understand that that's not really what I want to do with my life. Like, I think it was a Nokia project that made me rethink like my life. We were working for Nokia on Witsets, which was back in the day was one of the biggest mobile services in the world. And we were sort of the design agency, and I was working on that project for like 2 years, and then they just shut it down because they didn't know how to make money with it. And that was sort of the motivation for me to rethink things and sort of wanting to take control of what I work on. And so I wiggled myself out of the agency, did a few startups in Finland, and then moved to China for a year. Like, we always wanted to sort of go abroad with my wife. And it never happened because of the agency. And now that I got out, I was able to go, lived in Shanghai for a year, doing games and toys and animations for the local market. A small startup of like 250 people. It was weird working at that time in China. Culture-wise, super interesting, but professionally, maybe not so much. And then I got the opportunity to move to San Francisco to join Groupon, which I obviously took as an engineer. It didn't really matter whether it was Groupon or something else. Like, I got to Silicon Valley, and that was awesome. I spent 2 years at Groupon building a point-of-sale application for high-end restaurants. And, Groupon wasn't really the engineering powerhouse that I actually wanted to sort of get experience from. So when I got my career card and was able to freely select where I wanted to work, and I switched over to Uber and spent 5 years on the mobile platform team at Uber, trying to scale mobile engineering. When I joined, we were 15 mobile engineers at Uber, and when I left, we were 400. So it was a pretty wild ride. Going through that, seeing hypergrowth, learning that I never want to go through hypergrowth again. And after Uber, we started Linear together with Kari and Jory. So that's a very brief intro into what I've been doing. In my sort of personal time, I don't really do much. I've got a family with 2 kids, and I do some glider piloting. So
nice.
I go flying on the weekends when it's good outside.
That's fun.
Oh, cool.
How was the experience of scaling at Uber? How's that shaped your time at Linear? How does that approach how y'all do hiring and everything else?
It was a good experience. Like, it's good to go through it once, sort of to realize, because there's a lot of sort of work that goes into scaling a company that rapidly, and you see all the problems at the same time, and you sort of have good stories after those few years of hyper growing. But I sort of did realize that and I think Kari maybe went through something as well in Airbnb, Coinbase for certain, went through the same things, where like the problem with hyperscaling is that when you have a product that you don't know whether it will find product market fit, you just try everything, and you don't really care about any of the engineering or any of the technology that you work with. And your architecture is probably total crap. And everything that you do is sort of throwaway work, it seems at least. And then you suddenly hit product market fit. And now you're suddenly in a race with somebody else, and you need to scale quickly because otherwise the other company will overtake you. Sort of the same thing happened with Uber. Like the architecture that they had was just really crappy. All the servers were down all the time, and when sort of growth happened, it was literally fighting fires for 2 years. I thankfully wasn't on the back end side of things, but I did see how sort of burned out everybody on that side was, because literally for 2 years they just week after week they encountered new problems that they had to fix while everything was growing. So they had to hire a ton of people. And after 2 years, like, you had suddenly 2,000 engineers. You had everything was burnt down, everything was on ashes. All the teams were burned out, and then sort of the growth started slowing. So you had a little bit of breathing room, and suddenly you realize that you've got all these engineers that you've hired because they need to keep up the lights. You have nothing in terms of infrastructure because everything's just been put together, and now starts the project of like let's redo everything. Let's start from scratch and figure out like what we actually want to build, and in the next 4 years. Is going to be that. I still, like, when I went back to Uber, for example, this January, to see my former team over there. They were still working on the same things that they started when I left. So it just like crazy how much time sort of gets wasted in hypergrowth. It certainly makes sense for many companies, and Uber shouldn't have done anything differently. Like, if you have a product that is that you don't know whether will sort of find consumers or customers, it doesn't make sense to build architecture. But the way we started Linear, what was totally different. Like, we knew that the customer segment was there, and that the market was there. We thought we would be able to get product market fit really quickly and easily. Like, it there was no question about it. Whether we could build something better than what was out there. So we just took the time to build out the infrastructure first, and make sure that we can build on solid infrastructure from the get-go. And ever since, we've had the same philosophy. Like, we don't want to overhire, and we want to be super sort of strict about hiring. Like, we want to say no until we find somebody that we're super excited about, and until we really need somebody to help us out on certain fronts. So, for example, on the infrastructure side, like, we're building the entire infrastructure of Linear with 3 people. It's me and then 2 others that sort of work on everything related to infrastructure. And we do think that, by the end of the year, we'll have everything in place to scale infinitely, where we sort of, have, like, you can always optimize, you can always, make performance better, and increase the developer experience. But we think that we'll have the sort of big hurdles covered by the end of the year. And then maybe it's going to be like 2 people or 1 person on the infrastructure side to keep up the lights, because we want to make it a product problem, not sort of an infrastructure tech problem.
That's super cool. So before we dive more into those problems, for our listeners who don't know what Linear is, could you tell us what Linear is and why you guys built it?
Linear is, a better way to build software. We started off as an issue tracker, and maybe, going a bit into history. Like, we always wanted to make Linear a tool that would just make companies better at building software, whatever goes under that umbrella. And you obviously have to start somewhere. And we started with issue tracking because that was sort of what most of the smaller companies need when they get started. And we wanted to start, building out the tool with smaller companies, because, when you work with startups, they're usually, super vocal about, what they want. They're easy to talk to. They give you feedback all the time. But the idea always was sort of to, graduate from that as the startups grow. So do their needs in terms of software, what they need in order to build better software. So, over time, we've made the product sort of, footprint larger. And sort of gone away from just being an issue tracker into being a project management suite. And more is to come. Like, we want to build it into sort of a full-fledged suite of tools that, help you be better at building software.
Let's dive into the sync engine a little bit. So we asked Jory this back in episode 44, specifically is like, why offline first? And one of his big reasons that he gave was performance. Is like performance being a first-class thing. But I also want to frame that question to you. So building a sync engine where you can like work offline or more importantly, get the optimistic updates that like Jory mentioned is a non-trivial technical problem to tackle, especially when you're just starting a product. So why did y'all make that decision and what benefits do you think it gave?
Initially, we didn't make it for the reasons that we now want to continue using it. Initially, like the idea was simply performance. Like we've never wanted to make the product fully offline. That wasn't the intention. It happens that it works fully offline if you want to use it, but that wasn't the intention. Like we do think that people will be connected most of the time. There's a few cases where, like, if you're on an airplane, it would be awesome to be able to sort of read through your issues and maybe even create an issue and comment on some of these, and then sync them back up when you get online. But that's sort of a side case. That's not the primary use case. Literally performance, being able to offload most of the searching and the sort of page loading onto the client computer, not having to go over the network, just felt like a great way to build a very performant application. And that's initially how we started to look into the sync engine. I've got a bit of experience with sync engines. Like this is my fourth one that I now wrote with Linear. So I knew what I was getting into. And I had never, at Groupon, the sync engine is still in place, so it still works. And that was offline as well. So you were able to sort of take, swipe credit cards and take orders while you were offline and then upload them once you regain connectivity. But I had never sort of before Linear, built a very complicated and full-fledged application, on sync. But I always had this idea that sync felt to me like, optimizing the developer workflow as well, making it easier to build applications. Because like if you take the sync engine, like if you have the sync engine in place, which is a hard piece of technology to write, what you're left with is essentially a local client. Like you have a local, data structure that somehow magically gets synced to your local computer, be it IndexedDB or then, even into memory. And all you need as a product engineer, you just need to manipulate that local data structure, and everything else is taken care for you. Synchronization and real-time, aspects of the application are really, a non-issue because it doesn't matter whether you make those changes or somebody else over the network. If the sync engine just updates your local data structure, like your UI will just follow and update itself. It leads you to have to implement functionality in sort of an optimistic manner, where you assume on the client that most of the operations that you do will not fail, and you guard against that. Obviously, there's maybe a few cases where they might fail, or your data might be updated once it hits the server. But most of the time, like 99.9% of all operations will just go through as they're applied on the server, and the client will sort of make the validation and make sure that the data was correct when it got sent as a transaction to the sync engine. So essentially, like there's a whole swath of problems that you can just take out from the engineers. And that was the realization. Like we didn't start off building the sync engine because we wanted to ship features quicker, but we pretty soon realized that was sort of the main point that we got out of it. We did obviously get the performance for the end user, but then we gained the ability to just write functionality super quickly and just iterate on the product very rapidly, because you didn't have to think about networking or making connections or error handling or any of the real-time aspects, or even offline. You just had you have your local data structure, you make changes, and that's it. It becomes such a simple model to build applications with, that I don't think I would ever want to go back to anything else. It lends itself obviously to only certain aspects of applications. Like if you have a app that has tons of data, sure, you can't load up everything locally into the clients, and it needs to have some sort of collaborative aspect to it, because otherwise it really doesn't make sense to load up everything and do even synchronization. But if you have sort of a finite set of data in your workspace and it's collaborative, then I don't think I would ever do anything else than sync from here on out.
So you mentioned that this is your fourth sync engine. That's a lot of sync engines down.
Yeah.
Would you say that the main difference between like linear sync engine and those older ones is scope, whereas in the past ones, it seemed like maybe like only like one or two features were kind of driven by it, whereas with linear, like all data is driven by this live sync?
Not necessarily like scope in the way that we have lots more data in the client that we present. But to give you an idea of what I've built before, like my first sync engine was in China when I was working for a gaming company. They had a gaming portal and they were creating sort of Flash. I think it was Flash and then Unity games. And most of them, like they wanted to create real time player games. And that is, back in the day, it was pretty hard. Like units didn't really have any good multi-user servers, which is obviously what you use today because they built out everything for you. But we didn't. So, I created my first sync engine back then, which had a Flash client and then a Unity client. And it was essentially there to sort of synchronize game state. So, real-time locations of your users. It could, interpolate between, sparse updates. It would work with a slow network as well, and it could take quite a few hiccups in network latency because the network in China wasn't really that great. Like you regularly had a ping of like 600, 700 milliseconds to the server. So that was my first one. It was one small arena with max 16 users connected to each other and sharing a few property updates of essentially locations of the avatar moving around. Then in Groupon, I created an Objective-C client and a Node backend. And that was sort of much more sophisticated, but, built in a very sort of hacky manner. I don't think I was a good engineer back then when I joined Groupon. So I did all kinds of mistakes, like no unit testing on any of that stuff. And it was written in JavaScript, nonetheless. So no type safety at all anywhere. So it was a bit... a bit unstable at times. I think they rewrote it now, but I'm sort of keep on hoping that they still use it somewhere. And that was synchronizing essentially like the entire state of your POS between one restaurant. So I was working on Breadcrumb, which was sort of a point of sale for high-end restaurants, where you had multiple iPads in a menu. You would take orders, you would swipe credit cards, you would send those orders to the kitchen. And it was important that, when you sort of, took a credit card that you wouldn't sort of double charge the user. So all the iPads would need to be in sync. It was very similar to like what the game engine was, but just a bit more sophisticated in like it had rules around like who can update these objects, because it was, again, important to sort of retain, access to an object before you, for example, to the bill before you started charging it. So it was just a more complicated version of it. And to some extent, like the linear sync engine works in a very similar manner. It's just sort of another iteration on top of it. In between, I wrote a sync engine for Uber as well. It did see the light of day. Like it was used in one product in New York as sort of a trial bed, but we had sort of big ambitions for it. But, I think I was a bit too late. Like hyperscaling started happening was already happening when I joined. And it was, almost the first project that I undertook. I was like, sync is great for this use case. Like if you have an Uber client, what Uber was doing back then, it was pinging the server every 4 seconds and retrieving the entire state of the world as a JSON blob, which was like 50K of data at some point. Every 4 seconds, it would retrieve it and then display it and retrieve it and display it. I was like, man, this is not great. I know how to fix this, and I know how to build a better version. So build a sync engine that was, there was a small team of people that built it. There was a Go backend, then there was a Swift client, a Android client, and a JavaScript client. So 3 clients, because we had the intention of sort of moving all of Uber onto that sync stack. And we were in the process of sort of, making the data schema work with sync, because there's certain aspects that you have to do in order to make it work. And at that point, I sort of realized that, the whole of Uber is moving too fast. There are too many people. Like you can't sort of force this upon anybody. And there's really no use case for the backend engineers to, take it on. And many people just didn't understand what I was doing or why it was so much better. So it was sort of an uphill battle. And then, I started doing other things over there. The mobile platform team got formed, and I started hitting that. So yeah, I mean, I was maybe a bit late to the party. If I had joined a year earlier, there might have been a sync engine in the Uber client, and the world would be much better off, because it took them like 4 years to come up with all kinds of concepts to make that ping sort of smaller, and in the end do some sort of real-time connection from the server to the client that was very very lightweight and very brittle. So they really could have used that sync engine. And it actually got open sourced. I think it's still out there. It was called Jetstream. If you want to have a look, it was never fully developed, but at least there were like three NAS clients to it. So yeah, then back at Linear, I hadn't done web engineering for ages, for 5 years. I had just been doing mobile engineering. So I the first thing that I wanted to do is build another sync engine, and now on the full web stack, because I hadn't used it for a while. And I was keen on trying out like how the toolchain has evolved, and how quickly you can come up with a sync engine. And it took me a weekend, and I had sync up and running on Couchbase. I think was the first implementation on the back end, and that's how I got excited about the project. Like, it wasn't really issue tracking that I wanted to do, or project management. And I think Jory felt the same. Like, we always thought that issue tracking is kind of a boring space to be at. And it took us a while to understand that we're not really working on issue tracking, but we want to help companies be better at building software. But at least I got excited about sort of the tech first, and building out a sync engine.
That's awesome. Real-time technology has evolved a lot over the years. Just the research has evolved a lot over the years. So there are definitely a lot more like off-the-shelf CRDT implementations. So I think of like auto merge from Ink and Switch these days. So you mentioned CouchDB, which had its sort of own sync mechanisms built directly in, right? So I could see how you could get up a prototype really quickly for that. Mm-hmm. For the sync engine that you have today, or sort of what you've been working up to, do y'all still lean on CouchDB, or have you taken a different approach and done things more custom? And sort of a follow-up to that is like, have there been off-the-shelf libraries that you've been able to use that you found helpful for doing this, or have you had to really sort of like dig into this and do a lot of custom stuff?
Yeah, we've had to build everything ourselves. There's nothing existing in the sync engine. Well, now we start to use YJS for the last sort of feature that hasn't been real time, which is sort of editing issues or editing large documents. And now we're finally putting that into place. Hopefully we'll have it out, not soon, but soonish. But apart from that, yeah. So the first trial was with CouchDB, just to get something up and running, and you immediately like you hit you hit problems very early. With CouchDB, it was access control. Like, there just wasn't any access control. CouchDB, at least back then, was really designed to synchronize settings for a user, and it wasn't meant for a multi-user environment. Then the second prototype that it was on Firebase, and Firebase would have probably worked nicely, but I did some calculations at some point on like anticipated user counts and how many updates there are and how much we need to load data, and it would have just cost immense amounts of money for our intentions on how we want to manipulate the data. And yeah, I guess I always had the intention of building a custom one, because I had done it 3 times before already. All of these were custom implementations, so I wasn't really afraid of starting on that and sort of running against anybody. Like, we had time. We were still sort of working our day jobs when we sort of trialed this on the side and built a few prototypes. So yeah, I think today, if I started, I don't know what I would do. Like, I would probably start with an existing off-the-shelf solution. But I would think that I would run into problems at some point again, which would, have me switch to a custom one. There's just so, like, if you think about like what we've done at Linear to optimize the user's journey in the application, to what we load at startup, what we don't load at startup, how we handle all these problems that we faced. None of the solutions offer that, or they shouldn't really offer that, because those are really custom to our application. Like, there's nothing generic that you could put in place. in order to, create a sync solution that would work with any kind of application. Maybe at some point somebody will write one, but they'll probably have quite a few startups under their belt. They've seen all the problems in order to be able to anticipate those problems. So I don't think that any of the solutions currently would today work with linear.
Yeah, out of curiosity, so there's the engine, which is the comprehensive solution, and there's a lot of business logic in there about what data you load and how you handle conflicts and a lot of that stuff. But there's some core data structure. Are you using CRDTs for that, or are you using just like custom data structure, custom semantics to deal with like conflicts and things?
Everything's custom, as I said before. So no CRDTs. Most of the operations that you do on linear, they don't, like, CRDT doesn't lend itself to it. Like, they're atomic operations. Like, if you change the priority of an issue, like, it's either this or that. Like, it's not in between. There's no merging that you can do. Like, literally the merge is like last one wins. Like, if you said it first and the second person comes after that, the second person wins. There's only a few fields that have sort of textual input where you could use CRDTs to sort of, do conflict resolution. And that's where we're putting it in place now. Like, we do it as an addition. So far, for example, if you've, edited the description of an issue or a project, we've for 3 years now, we've been like, well, damn, we really need to fix this because we don't feel comfortable with the solution that we have, which is like, you write it locally, and then when you unfocus from that text field, it'll get updated and overrides anybody else who's made any changes, which sounds horrific because you might be writing for quite some time. But we do save it in the meantime to sort of give you an indication that somebody else might be editing it at the same time as well. But it's still like you can easily override people's changes. Yet it almost never happens. Like, just like in an issue tracker, it's not that many people will write. We'll look at an issue at the same time, let alone, update the description of that issue. So it hasn't really been a problem. Like, we've always wanted to fix it because we think that, using CRDTs for that issue editor would just be a much nicer experience. But, it has been sort of pushed along because, like, we've had more important things to work on. But now finally we're getting to it because we do want to use the editor for even larger documents than issues where we do anticipate that there's, a bunch of people will want to edit it at the same time. So we need a good collaborative editor where we can have like the whole team jump in and sort of make edits at the same time. And then CRDTs are perfect. But everything else, yeah, like the whole data structure that we have is essentially just a tree of data, of JavaScript objects. And we do, quite a bit of work in order to, hook that tree up together. Like, if you have listened to my 2 talks that I've done on the sync engine, like, to sort of give you a bit of an idea of how it works is, you get individual objects. Like, every single model object is just an object that gets sent over, and the decorators on the classes that represent those model objects, they tell where they should be mounted on. So, for example, an issue will have a team ID associated with it, and a decorator saying, this should go into the team's issues collection. So when you receive that object, the sync engine will look like, whether we have that team already loaded. And if we do, then it will go into the collection and add that issue into the collection. So it builds out that tree over time as you stream in your objects. And that's how you get to that tree. So you can either look at, all the objects in sync as individual objects, which the sync engine does, or then you can, construct a tree of model objects out of that representation, and that's what end users use, or end users as in engineers.
So that's like the basic how it works. Like, mostly you have this pool of objects that gets created into a tree, and that tree is used to update the UI.
Yes, as a very sort of that's how it works. There's nothing more to it. So the sync engine literally has 2 jobs. Like, it gets the user up to date with the current state of the world or all the objects that you as a user see, and then it keeps you up to date. And there's humongous complexity around both of these problems. But in effect, what happens is when a user comes in for the first time and doesn't have anything on disk and logs in for the first time into linear, We make what we call a bootstrap call to the backend saying, give me all the objects, like everything as a JSON blob. And the server will look at like what the user sees, what the access control says about like what objects, the user should have, combines it all together and sends it over to the user. The user then, creates model objects out of each of these. Well, here it gets a bit more complicated. It doesn't, put everything into memory, but at least it stores everything on disk. So the disk representation has everything that the user has received so far. And then when we start accessing that data, that's when we create model objects out of the representation on disk. And that's what gets bounded to the UI. So we do load up quite a bit of data up front from the get-go, like all the objects that aren't that plentiful but are important, like the workspace and all the teams and the users, the labels, everything except essentially issues, attachments, and comments and issue history that we keep on disk and load it when we need it. And that's how you get to sort of the first representation and the first rendering of your UI. And now you can refresh at any given point in time, because on disk we already have the whole state of all the objects, and we can load them up. And at that point we do take a WebSocket connection to our sync engine, and then we start receiving data from that sync engine. Like we tell the backend like what is the last sync packet that we've seen. Like every packet in the entire organization has an ID, which is the counting number upwards, and then the sync engine will essentially send you all the data that you haven't seen and keep you sending stuff. And as it comes along, the actions that are applied are essentially insert actions, like when new objects are created. They might be update actions when objects are updated, and then archived and delete actions, in addition to a few others like that tell you like that your sync groups, for example, have changed, which we use for access control to let the client know that there might be more data that you need to load from the backend because now you were, for example, added to a private team. That's in essence what the sync engine does. Like whenever you refresh, we try to figure out like what we need to load. We load it all, store it on disk, and then load it from disk into memory, and that's what you get as an engineer. And then there's so much complexity around these problems, because the first implementation that we had lasted us maybe half a year until we had like 200, 300, 400 issues in a workspace, was to just load up everything into memory when we go to the workspace. And then we started seeing that that's actually a pretty slow operation if you have lots of objects. So then, we needed to optimize. And I guess we've done 10 pretty major optimizations to the sync engine in order to get to the performance that we're at now. And we haven't sort of, completed everything yet. Like we're still rolling out, hopefully, the last of these optimizations that will get us at least, 2 years more time to think about like what the next step is. The thing that we're doing is like we don't want to load up sort of all the issues even onto disk. Like so far, when you've come to Workspace, you load up all the data. Like you get a bootstrap that contains everything except for comments and issue history. Those were easy to sort of load later as needed. But now we're doing the same thing for issues and attachments, because those are the next huge objects that people will have. And we're leaving those out. Like we load none of them, and we make it all dynamically loaded. And the big problem there is that you see issues everywhere. Like they get rendered literally on every single screen. You've got calculations, you've got aggregates of like what the issue count is, or how many items you have in your inbox, or whatever. Like it is everywhere. So we needed to build a very complicated loader that lets you essentially stream in all the data that you need. Where the UI just can request whatever. It can say, I need, all the issues for this team, and then I need all the issues for this user. And there's a, centralized place that will then dedupe all these requests coming in from all the differend areas of the UI, and then create an optimized batch request, make that to the network, and load up, everything in one go, so that we don't hit the, backend, 200, 300 times as we otherwise would.
Interesting. When you were talking earlier, you mentioned a packet and a packet ID, and I was like, all right, you have like an aggregate log of packets, which are probably like deltas of things that have changed over time that you can just like, hey, this is my last state. Give me the other things that I need. But when you're talking about like dynamic streaming, you're like, Well, I guess maybe that's not actually the store state. This is just like I want to prefetch X list of things or X category of things, and you still have your like packet ID of like this is my latest state. This is the world that I know about. So those are, I guess, separate sort of forks.
Yeah, they're separate. Like obviously, the main database will have the latest version of all these model objects in. So when you make a query to the backend and load up, say, all the issues for a specific team, you get almost the latest version. And that's where the complexity kicks in. Like, you get a snapshot in time, but after you get that snapshot, you might have other sync packets or changes that are exactly being sort of mutated in as you're making that one request to the data. So you have to figure out how to keep everything nicely synchronized, and so that you don't override changes that have at the same time streamed in. And it's not too complicated, but it required us to find these issues and figure out like all the places where we might have race conditions, and then take that into account. The easy solution there is like, yes, you load up, in batches, you load up, an arbitrary amount of data, but you don't store it on disk if you have it already on disk. Because essentially, like once something is committed to disk, that means it has come from either a bootstrap call or a much more recent sort of sync packet that has streamed in as people have been making changes. So if you've written that to disk already, then the disk version will be newer than what you have in your in your batch. Maybe just don't override those changes. And then because you do that, you can actually start taking snapshots that might even be older. You don't really care. Like there's certain, like you need to be aware of what the client has seen already in terms of sync packets. Like if the client has only seen the last the last 20 minutes of sync packets, then you can't load from a snapshot that is older than that, because otherwise you might be loading old data that is incorrect because the client hasn't seen all of that. But if we know that the client has seen more, or has loaded a more recent version of that, it doesn't matter how old the snapshot is that we load, so we can go to a cache. We don't have to go to the main database, and we can sort of optimize the backend with that as well.
So I was watching your recent talk on all the changes that you did for this, and it was fun to watch you like move the fire emoji across the stack to where you moved the problem to. I found a few of those problems interesting in that the technology choices that you had to make to fix the problem. So the first one was the, GraphQL. Originally, in like the first version of the sync engine, it seemed like you relied a lot more on GraphQL to do a bunch of the stitching. Can you explain like what GraphQL was doing, why you moved off of it, and what you moved to?
We actually moved to GraphQL to fix some of the problems that we had. So the story of GraphQL is like obviously we could have had the sync engine sort of also handle all the mutations, like using WebSocket connections. But what we already knew in the beginning, that we wanted a public API that people could hit as well. And then you need to use some kind of standard in order to achieve that. And we wanted to go with GraphQL. So we built all of our mutations on top of GraphQL. And then it really didn't make sense to sort of build all the business logic twice, like once for the sync client and once for GraphQL. So we ended up with a solution of, saying that the client will just hit that same GraphQL endpoint as a public API user. And then, aside from that, you get a second pipeline of all the changes streaming into the client. So if you make a change on the client, it will actually hit a GraphQL API endpoint. That API endpoint will then write all the mutations or all the changes to disk. And as a result, which is also part of the public API, you can query that. It will send back the last sync ID, which essentially means like the last change as it got added to the queue of changes that happened with that mutation. Because again, the mutation might make hundreds of other changes at the same time. Like your input might affect other properties as well, and that is sent back to the client as a response. And then the client starts waiting on sync and counts through all the packets that come in until we hit that number. And then at that point we can say that okay, the transaction has been completed, and that request is now done and applied to the local database as well. So there's a bit of playing with, GraphQL, to send the mutations and listening on the results on the sync engine. But that's what we chose in the beginning. And in the first iteration, what we did was, because of all these race conditions that you might have, like when you catch up with the user. So if you have some sort of state in your local database and connects to the socket server, you might be behind 1,000 packets, for example, and you need to catch up with those before you can connect to the live stream of packets in order to sort of, you need to apply all the packets in order, because otherwise you might get out of sync. You might, write a update that was done earlier, on the changes that were, you might get out of date with those packets. So what we initially did is, when the client connects to the WebSocket, the WebSocket would then load up all the changes that the client needs to see in order to catch up, and then send them to the client and then continue normal operations. But the socket server would have to stop the world while the client was waiting for those changes, because, otherwise we would have to have, queues for each individual client to figure out whether we can send these updates now to this client or whether that client is still catching up. And that would be just a complicated sync engine. So that was the first implementation, and one of the first problems that we had was that stopping that world was just making everybody just wait for a client that connected that had to catch up with a lot of packets. So we got rid of that, and we put that onto GraphQL, because GraphQL was actually we did then replace GraphQL as well. So first we moved it to GraphQL and said, hey, GraphQL, give me all the changes that I haven't seen, and the GraphQL response would then send you 1,000 Delta packets to catch up, which is fine with 1,000 packets, but then you got into tens of thousands of packets. And now suddenly your response was so big that it would just crash the memory of your GraphQL servers, because you would have, hundreds of clients doing it at the same time. And those packets, they consume memory, because you've got them in memory 3 times. First the database load, then the JSON, and then whatever you put into the pipe. So then we got rid of GraphQL again. And we moved to a REST endpoint, because we could implement streaming on top of that. So we moved both sort of the full bootstrap and then the delta syncing, so the catching up onto that streaming REST endpoint. So the client would hit the endpoint. The endpoint would then take a streaming connection to the database with a query, and as the database would respond with objects that fulfill that query, the REST endpoint would stream them to the client and then immediately forget. So it would just pipe through to the database, and that made things faster, as well as much more memory efficient, because you wouldn't, in GraphQL, you have to wait for the entire response and nicely package it up and then send it to the client. So it doesn't work well if you have a lot of data to send.
You have a lot of really interesting problems here. So, given that you have an API and you're sort of aggregating a bunch of events that are coming from clients, and you're likely having to sort of normalize those in some ways. So if people are hitting the API, they can say, hey, I want the list of issues, the latest issues from this project or whatever. You have to be able to serve that, which ultimately means, likely your database on the back end has to have some normalized representation of what your business data looks like. Whereas, and you'd mentioned earlier that the client has its own view of the data. So a lot of the project engineers are only really thinking about how is the client storing this data, and what is the, I can sort of access this locally and just forget that there is a back end. The sync engine will just take care of it. So how do you manage the complexity of having to sort of define this data in multiple places? Do you try to, how do I best ask this? Is it do you try to just have the same schema in your data store on the server as you do on the client, or do you just handle it on a case by case basis? It's how do you avoid inconsistency there?
Yeah, it is all the same. The data representation in the database is the same as the object representation on the API, which is the same as the GraphQL representation or the GraphQL schema, which is the same as the client schema, with some differences. So we use TypeScript for everything. So on the API side, it's easy. We've got one definition for we call it a client entity is, and it has a bunch of decorators. One is the decorator for the database representation. One is the decorator for the GraphQL representation. And out of that, you can generate both schemas. So you write it once and that's it. We wish we could sort of, automatically implement the client representation as well. But as it turns out, like it's not really a big thing to write it twice. Like we just copy whatever we synchronize over. We name the properties the same, and on the client side, you have a bit different decorators because you need to stitch it up in a different manner. And obviously, the business logic might be very different between the client and then the API. But the data representation and the property names are the same. So we don't do any translation there, which, if you look at our GraphQL API, means that it's not the best GraphQL API. Like it's very raw. And that's sort of, the bad side of doing this. But, it just keeps things much simpler and lets us move faster without having to sort of transform the data or keeping multiple schemas alive. So that's how we manage it. Like TypeScript helps us immensely with that. And we do have certain decorators on the API side where we can say like, this property is not part of sync. So it will never be sent over to the client. So you can have some hidden fields in there, like secrets or API tokens or whatnot, that just exist on the backend and never get sent to the client.
So another step that I found interesting on your fighting journey was what you chose to do with the database. At first, you had a replica, and then you moved to a second technology that I probably wouldn't have chosen myself, but I found pretty interesting. So how did you fix your database problems?
Caching, yeah, that's usually how it works. Yeah, we had a big problem with the full bootstrap because the logical representation of that data in the database is just like it's a relational database. We use Postgres for that, and if you want to query all of the data for a client, it's a huge query. The client might receive anything. If you unzip everything, it might be even 100 megabytes of data that you get during a full bootstrap. So querying that together with other users on a relational database just doesn't work. You can't have enough memory to fit everything into memory to make that query fast. So we wanted to cache the data because, again, like we know that the clients can already catch up. Like they can make a delta sync, say, I've seen up until here, just give me the rest through delta sync. So we can take a snapshot every now and then, save that in some cache, make it somehow queryable so that individual clients can still receive the data that they have access to, and then just try to make that as fast as possible. And we actually tried two technologies. Like we're all on GCP, so we the first implementation that we wrote was Bigtable using Bigtable, because it felt like we want to normalize, like all the data was already JSON serialized into that. Into those rows. So we were just sending strings over. So Bigtable felt like a good idea. And then it felt a bit slow. It was like, why is this taking so long? We did all the right things, and we don't even have that much data in there. So we did a second implementation on top of Mongo because one of the engineers had used Mongo before. So he was like, I can just write some up. So we initially wanted to just get a benchmark of how slow are we, and whether Mongo, how much slower would Mongo be. Turns out that Mongo was like 3-4 times faster than Bigtable, so we stuck with it. It's like we use Mongo for literally a cache, like it's caching serialized versions of those model objects, and now also the delta sync packets. So that it becomes very easy and fast to query those out. So we can cluster them much nicer together, and fetching a lot of objects is super fast.
That's awesome. That's a really interesting use case. I think you probably are able to avoid a lot of the sort of warts of Mongo if you're have a relatively like straightforward usage. I mean, it is a pretty fast database when you're just doing reads. Turns out.
So we've talked about like all the technical complexity of the sync engine and the back engine, but we haven't touched on what it's like as a front end developer to consume any of this. So like my two main questions would be like, what does updating the UI look like? Do I have to care about it as a front end engineer? And what does updating data look like?
Yeah, I mean, both answers. That's super simple. You don't have to care about updating the UI. That is handled automatically for you. We use MobX for all the UI updates. So literally one thing that you need to remember is just, put an observer tag or observer function around your component, and that's it. whenever that data changes, your component will be re-rendered, and there's nothing you have to do outside of that. So every single property on all the model objects that you touch are either getters or observables themselves. So if any of the UI touches those properties and then they get updated either by the user or via remote call, then the UI will just update automatically. So there's nothing you need to do. You just render your stuff, and that's it. And if you want to change things, you just change them, and then you have to call save on that method, and that's it. Some nuances, like if you want to make sure, like there's some cases where that don't really work nicely in offline mode. Like creating a team in offline, it seems like a bad idea because we don't know how long you might be offline for, and there might be another team with the same name. So then that operation would fail, and by that time you've created 100 issues in there. So we don't want to do that. So there's ways for you to detect those in that save method when you call. You get a transaction back, and you can listen whether that transaction got offline. If it did, you can cancel it and display an error. And there's ways of handling errors as well. Usually the sync engine takes care of showing you all those errors as well, because they're usually very generic. Like if you have an update operation, we know what you're updating, and we can give you a nice toast on, failed to update issue. And then, the error message will be retrieved from the GraphQL user error that we can put in the backend. So usually you get nice errors as well without you as an engineer doing anything. And that's it. Like, you have the structure, you render it out, and when you want to send transactions, you just change the data and call save. And that's all you need to know about sync if you're a front-end engineer.
Beautifully simple.
It's pretty awesome. We do, and as an industry, we do tend to spend a lot of time and complexity on the boundaries between services. So having worked on the mobile app for a while, I'm sure you felt this very strongly, is that, thinking about how you interface with your API and how you change your API and those interactions, especially with mobile, like versioning and stuff like that, becomes a really, really heavy complexity. So this is just like a really interesting and refreshing sort of approach. We've seen a lot more backend for front ends that are trying to make the API layer more and more seamless. So I don't know. This is just a really interesting perspective there of like how both a sync engine can benefit you in giving you all these more features, but also just making the integration to the UI a lot more seamless.
Yeah, I totally agree. That was one of the learnings here. It's not, it started with performance, but then it became sort of the secret sauce of the company to be able to ship that quickly, because you don't have to do all these things.
Awesome. With that, let's move on to tooltips. And that wraps it up for this week's tooltips. Thanks for coming on, Tuomas. This was a really interesting deep dive into how linear sync works, and I myself am inspired by it.
Thanks so much for having me, Justin and Andrew. It was awesome.
Yeah,
sharing a bit of this stuff, and hopefully, people should really get interested in sync and get inspired and start building their own sync engines or use some existing tools. Just use sync. It's so much easier to build. Like if you have the correct, if you're building the right application that lends itself for sync, you won't regret putting it on sync.
Yeah, so awesome to hear about it, and this just reinforces to me the sort of care and technical excellence that goes behind building linear. It definitely shows through in the product, so it's so cool to hear about.